It's not like a huge problem, but I think it's the kind of tiny thing that can improve a lot of things. So the main way we're going to talk about it is like, hey, I have Bobby. Bobby wants to make an application, like he needs a way to store pictures. So here we have like a possible endpoint where he enters a user and he wants to put a profile picture, and he needs to know how can I send a profile picture from my application to the clients on the browsers and desktop client and everything. So the first idea is that's like you can have this, let me just put the data right here, and it's quite smart because like you literally just send the data along, but it doesn't scale. Like if right now I'm saying to you, oh, I want to send like a video file, as that's 20 gigabytes. You probably don't want to send that every time in the JSON. It's expensive in the sense of like now you cannot do optimization of I'm going to use the cheaper CDN from my image and have the RPC that's fast. And you don't have caching, which is a thing that helps you a lot with cost and generally like how companies do. So the usual solution is let me put like a URL right here. The URL works, but it essentially locks Bobby in. Like if he wants to move the data, he also has to change all the URLs, which sounds easy when you're having an RPC server. But like if now I'm telling you, oh, this is a smart contract, and the smart contract is linking data, updating all of it could be expensive. And caching is like hard. You're supposed to be able, if you use HTTP, you have eTag, which is supposed to work. But like getting this tag to work is way harder than it does. It locks us in like, we have to trust that the data we're getting from the server is correct. So usually we use TLS or something else like this to verify the CDN, which is giving data is bad. And what I want to tell you is like, hey, we should actually talk about the data. Like why, when we want to get a file, the first thing the usual way to do it is like, I'm telling you where to get it. I think you should tell me, hey, that's the file you want. And so to do that, we use hashes, cryptographic hashes. So I hope everyone here kind of know about them. Like quick recap, it's some math function, magic math, that takes bytes and transforms it in all the bytes which are shorter, usually of fixed size. And so it's kind of like compression, but it's one way. You kind of go back from the hash to the thing. But the point is you can use for verification. So the default way you use hashes is let me just hash my file, my big video file, and I put the hash at the end, and then I download all the data and verify it at the end. It works for tiny files, but for bigger files it has problems. Imagine I'm trying to verify that file and there's an error somewhere, and that's a 20 gigabyte file. I don't know where the error is because I'm only able to check once I have the hash at the end. And so what we also want in content addressing is having Merkle trees or other data structure. Like, so what we create is we take the original file and we cut it in many pieces. We call them chunks. And then we create another new piece of information which we're not going to display to the user, but that lists basically all the hashes inside the file. And we take that hash of that, and that's the thing we give to the users. So the main point is that if, let's say, the user, this is a video file, and the user wants to stick in the middle of the video, I don't have to download the complete video file. I can just download the list, which is often very small, and jump directly to the block in the middle because the user wants to see the middle of the video. We can also do things where we download the video in parallel from multiple people, because now, if someone sends us bad data, we can be able to track precisely where the file was the bad data and who give it to us. And lastly, incremental verifiability, very important thing. We don't, like, it's very bad UX. If to view video, I have to download all of it first. And the good thing here is, when I download the root of the Merkle tree, the block that contains the list, and then I can download the first block, I already know this data correct. I don't have to download a whole bunch of stuff. So we are about to have a streaming verification. Now, another problem we have is like, okay, so both with location addressing, the way we do it usually with DNS, and content addressing is how do we find the data? So quick recap on DNS. Usually you have a client that asks some other server, we call them recursive resolvers. You ask them like, hey, I want to visit example.com. They check at the top level domain DNS, which tell them the IP address of the second level, .com, and then the last .com tells us about example, and we can ask example, what's the IP of the server I need to contact? On content addressing, we have a slightly similar problem in the sense that we cannot just contact hashes, we need IP addresses, and so we usually use distributed hash table. It's not only solution, but the way we do is we use all the hashes based on the identity of the peer to put them in some different data structure here, let's say a ring, and that creates a key space where all the nodes are sorted. And so what we're going to do is that I'm first going to look randomly at like the best peer I know, and the peer in the key space, they know their neighbors quite well, and the farther from them you go, the less they know. So at the start, we're doing big jumps from like this first peer is able to jump us to a second peer that's closer to the file we want, which jumps us even closer and even closer. And at this point, we don't usually get the file because it's like expensive. So what this peer does is that it's going to publish is like the node that has the file, and the final peer that's on the bottom right is going to remember, this node that just talked to me has this file. And so now when someone wants it, they can start in totally different region of the DHD, and they do the same jumping, and by the end they will join, they'll contact the same node that originally had the publishing. So this node is like kind of phone book. They know they know for like one small part of the network which people store the file you want. And the other solution that's often used is indexers. On Torrent we call them trackers, and on IPFS we call them IPNI. This is kind of one way you can use IPNI and IPFS, is that you do a publishment on some PubSub channel, and then the indexer, which is some federation of servers somewhere, is going to contact you and download all the CIDs you have. Not all the CIDs, a list of CIDs you have. And then the client can just ask the indexer directly. So it scales better, but now we need extra servers that maintain the big database. So various trade-offs between DHD and indexers. And in Kubo right now, which is the original DFS implementation I work on, which is do both in parallel. And like, at this point, if you're doing this, you're doing magic. Like, it's awesome because we completely decouple where the data is stored, how it's transferred, to the actual data we want. Like, if I tell you, hey, that's the CID of the data, and you're doing content addressing, so you're looking in the DHD and IPNI to find people, there's no reason that you have to find the same people that originally stored the data. So, for example, the way good applications of that are Torrent, for example. Torrent, very good peer-to-peer application, extremely efficient. And like one of the fun things I noticed is usually it's common, like computer science knowledge that, hey, if you want to post video, it's very expensive, transit is like huge, you have to pay traffic costs, and video are big. And I don't know, but like you look at Torrent, and it's very cheap, and it works very well. So it's kind of like, so the way Torrent does it is you download the video and then you reshare it, because when you reshare it, other people will send the file to you first. So if you reshare the video, you're gonna be able to download faster from multiple people. And yeah, again, because they have chunks, they can download in parallel. So if you have like 1,000 people hosting, downloading your file in torrent, then you can download at gigabyte, if not terabytes of speed. So you're not limited by the server anymore. You're really only limited by yourself. And also a good application of content addressing is Git. Git doesn't have the magic, oh, here's the hash and let me resolve it for you. But it's kind of, so it's slightly content addressing, like content addressing is on a spectrum and Git is somewhere in the middle. So the original point of Git was the Linux kernel was developing, they were having issue with tracking sources. And so Linux kernel is like huge. They have thousands of various maintainers that maintain the various subsystem. And they kind of want like a way for all the subsystem to collaborate without having to force any structure on anyone. Like they don't want to have, there is this one server you connect to and you can get and push code from. So the awesome part is that Git creates like a linked list of the modification, and each modification has points to a maple tree of the complete source at this point. And this means that if I want to like talk to someone that's working on a different module than me, I can just tell them, oh, I found this bug in like this commit, here is the hash. And even if the way they download it is like through 3 different servers than me, because we're using different servers on various modules to push the code, it works. And you cannot get it wrong. Like, imagine you get hashes, you verify the hash, and if the hash matched, even if the data flow through like completely different servers on the internet, you still know that you're actually talking about the same data. The last one, which is interesting, more in like cost optimization, is Docker. So Docker has this layer system. So when you build a Docker file, it's going to record checkpoints where you add like big changes, and every layer is hashed. And the point of that is like, for example, if I make a Docker that's based on some version of Linux for Kubo, and then someone makes a Node.js application on the same version of Linux, they can use, because we all use the same layer, the same original Linux layer, which is going to have the same hash. They can do caching. So for example, if you're deploying like Docker at scale, most often you have some big server in your data center that has a SSD for caching and very fast internet connection, and everyone downloads from them. And so like, if you download the same layers over and over, is it because you start the same Docker or different Docker that use the same image? You have like duplication in the sense that it's not everyone reaching out like over expensive internet fiber. It can stay very local in the data center cached. So like really performance and cost optimization here, because we use hashes to know if the data is correct or not. And so kind of like where IPFS fit in the world of content addressing. I talked to you about like 3 good content addressing applications I use every day in my life. But the problem is that they're not compatible at all. I cannot take my Git and easily put it on torrents. I cannot say, hey, I don't want like Docker to do like the local caching. I just want like this to be here. Just like let me do a kind of messy thing like torrent. And so it's kind of like Snowflake solution. Every time that someone wants to make a content addressing solution in the past, they're like, okay, let me start from scratch. And I think it's a bit of a waste, like mainly a waste in, hey, now you have to develop a bunch of things to get to the same place, while the things are really the same. Like we take hashes, you verify them, and you find a way to download them, or you find a way to download them, so content routing and data transfer. And there's open cost in the sense that it would be nice if I could just like say, hey, Docker Hub is way too expensive, but like there's this thing called like Filecoin that has cheaper storage. Can I just take my Docker Hub and put them on Filecoin? And I mean, maybe you could, but like it's going to be way harder than it should. And so IPFS is like, what if we made minimal protocols for content addressing, and we try to put them everywhere? They have to be modular because different people have various use cases, so you have to be easy to opt in, and that's like kind of great because all you need for verification is the hashes and the data structure, and that part is like absolutely not tied to the networking or anything. So it's kind of great on that point of you can do whatever you want on everything except the verification. So we really have to make the verification. That's the part where it's very important to have compatibility. And then on the rest, you can be, it's nice if we have compatibility because then we can send data between various implementations always. But like, it's not critical for the value here. And so the way IPF is doing it is we work on basic primitives, CIDs, which is the thing I showed you earlier, which is like, basically it's a hash plus a tiny bit of metadata that lets you change the hash algorithm, and a magic field, which is called codec, which tells you how the data is encrypted. We work on specs. We try to get alignment on specs and various implementation to support them in both in clients, so browsers, curl, Voxo, which is library we're working on, and mainly implementation on the server side. And finally, we provide like a library. We call it Voxo. It's written in Go. You don't have to use it, but we kind of, hey, if you're doing Go and you need like basic building blocks to work with content addressing data, you can use our IPFS library. Yeah, sorry, very last thing to how we're doing it. We have like awesome team, and it's hard if you like, we actually want the web to be using content address in the future. Like it's the real goal. So we kind of want it everywhere in the browsers, in all the tools you're using to download data today. And so if like you can make a solution technically, but getting people to merge it in their code is like radically different. And so that takes time, writing. But we work on it. We have people talking and very experienced people in how you get stuff actually merged. One last maybe side ideas, like I was doing this talk originally for another thing, so you're kind of my beta audience. If you have feedback, we'll love it. And I was like, oh, I need to add like a more blockchain thing. And one other very interesting application of content addressing is in the blockchain. So the first obvious piece of content addressing in the blockchain is your address that you use to send and receive funds, because it's purely created from the content. Like the content is the private key, which we keep private. And if I have the private key, I can create the address. I don't have to ask anyone else. The second thing is that it's cheaply verifiable. I don't need to download huge amount of data to verify that the public key is valid. If I see a signature, I can just use it. And the last thing is, so two main points. And so this is like the beginning. Like what is, you have addresses that are content address, but is the blockchain itself really content address? And I'm going to pull up an image that was from a paper. Oh my god, that's yeah. Do I really have 10,000 tokens? And it can be very important for the input to the apps. Like when you're communicating between the state on the smart contract and the state in your application content, it's very important that this is correct. And so what the very simple way is like we need to replay everything. So we need to dig in at the start of the world, download all the chain data, replay it yourself. So follow all the rules of, hey, this user sent this to this user, so now the balance needs to be removed and added. All those things that need to run code, and every transaction you have to rerun code, and it's very expensive. So what we do now is that the blockchain is actually just linking between state roots. So you can imagine this diagram as like the top thing is the Merkle tree for the state before transaction, and right after that we have someone that sent money to someone else. So we need to update one node in the tree for the balance. And so the way we do that is that we have the tree on top, and we're going to modify the bottommost node, like this one, and we're going to go up, because every node has the hash of the children. We have to update the node above, and the node above, and the node above, until we go to the root. And the root is the thing we're going to store in the blockchain. So this is like a tree that exists kind of side of the blockchain. And the way it works is we only have to update the value that we have changed. So most of the data is actually shared. Like all the right part of the tree hasn't been updated. So this data is like shared between the different states of the chain. And what this gives us is like huge compression of trust. So now the problem becomes to like, how can I validate the full blockchain? So how can I validate that the hash of this is valid? And we call that state root. And many blockchain like Celestia, Filecoin, Ethereum, Bitcoin, probably, I'm not sure about Bitcoin. Many blockchain does that. And this means that now you have like the problem of trust change for how do I validate anything that I get to how do I validate this magic number. And so there are details. You can do various things. You can ask, you can do with proof of stake, interesting thing. I don't really have time to go in details, so I'm going to go back to a very good paper on how you can do that.